Look, if the United States is losing the AI race, it's not because of chips, money, or even talent. It's losing because it's running out of electricity. Look, I'm Justin McShane from Geopolitics Unplugged.com, and today we're breaking this down into 4 parts. Number 1, why AI and semiconductors are really energy problems. Number 2, why fabs and data centers are permanent grid shocks. Number 3, why the U.S. grid can't scale fast enough. Number 4, and why this quietly becomes a geopolitical failure. Let's start with the core mistake. Section 1. This is a physics problem, folks. See, semiconductors and artificial intelligence are not technology problems. They're energy density problems. Every advanced semiconductor fab and every AI center creates permanent, non-negotiable baseload demands on energy. Once these facilities are built, they do not flex, they do not curtail, and they do not pause during grid stress. If the power stops, the facility fails. The U.S. is reshoring chips and deploying AI at the exact moment electrical grids seem least capable to support them. That's not politics. That's physics. Section 2. Semiconductor fabs are grid anchors. Take TSMC's Arizona expansion. 3 fabs, right? $65 billion, the largest semiconductor reshoring project in U.S. history. Each advanced fab location consumes 200 to 300 megawatts continuously. That's equivalent to a small city. Why? Clean rooms require constant airflow and filtration. EUV lithography machines can draw up to 1 megawatt each. High temperature furnaces never shut down. As chip nodes shrink, energy intensity rises, not falls. Reshoring doesn't reduce energy demand, it concentrates it. The CHIPS Act alone added over 2 gigawatts of new demand on the grid. That power has to come from somewhere, folks. Section 3, AI data centers are energy black holes. Now add in AI. AI is not software. AI is electricity turned into inference. Training a single large model can consume over 1,000 megawatt hours. Inference is even worse. It's always on, always scaling, millions of daily queries. Globally, data centers already consume hundreds of terawatt hours per year. With AI, that number could approach 1,000 terawatt hours this decade. Northern Virginia alone uses about 2.5 gigawatts today, headed towards 6.5 gigawatts by 2030, roughly 20% of Virginia's capacity. AI doesn't sip power, it guzzles it. Part 4. Look, the grid can't keep up. Here's the bottleneck. Demand is arriving in years, but supply arrives in decades. Transmission, 15 to 20 years. Nuclear, even longer. Natural gas, blocked by permitting and pipeline issues. The U.S. grid was built on a flat demand growth. It's now facing semiconductor reshoring, AI data centers, electrification, population growth all at once. Energy prices rise first. That becomes an invisible tax on AI and reshoring. Projects don't fail loudly. They stall. They relocate. They quietly disappear. The next section, why this changes like everything. This is not just economic, it's strategic. A nation that cannot guarantee its power to its most advanced industries cannot maintain technological sovereignty. It's just that simple. China understands this. It built generation, transmission, and industrial load in parallel faster than the U.S. can permit. The competition is not over chips. It's over who can supply electrons reliably enough to run them. Without a pivot to energy abundance, high density, dispatchable baseload, America doesn't lose the AI race dramatically. It loses it quietly through higher costs, development delays, grid crowding, and slow strategic erosion. That is the semiconductor energy trap, and it's already closing on us. If this kind of analysis is useful, we publish the Rapid Read Daily and deep dives several times a week at geopoliticsunplugged.com, where we get way deeper into this. If you want to support the work, like this video, subscribe below, and stay sharp with us. I'm Justin McShane. Thanks for watching, See you next time, and cheers.